Hello guys, and welcome back to part 2 of quantum devices and the blockchain. As previously discussed, we talked about how Shor's algorithm reduces the amount of time complexity to solve for a private key from its public key. We also talked about Grover's algorithm, which reduces the time complexity to solve a proof of work from a block. As Bitcoin is the first and the biggest blockchain, I'm going to be centering this video around that specific blockchain and discussing its vulnerabilities, etc. So let's discuss an attack a quantum device could perform on Bitcoin while utilizing Shor's algorithm. We could use this algorithm upon sending of a transaction to the transaction pool, where it then be processed and added to the blockchain. Once this transaction has been added to the transaction pool, a quantum computer using the public key that has been declared by the user sending the transaction can in theory solve the private key from the public key faster than it is added to the blockchain. This would allow the attacker to create a duplicate transaction directing the cryptocurrency to whichever account they want to send it to, essentially hijacking transactions while they are in the transaction pool. This attack is applicable to all major blockchain cryptocurrencies with some minor changes depending on how they implemented some things. Now let's talk about Ethereum, because Ethereum incorporates an account-based system rather than a UTXO-based system. This is a critical protocol change that makes a massive difference to its quantum vulnerability. Instead of being able to hijack a single transaction while they are in the transaction pool against a time constraint. Once an Ethereum account has sent a transaction, it must be stated, meaning the public key is publicly available. If there is any currency remaining in the Ethereum account that sent the transaction, then this account will be vulnerable until the key is recycled and a new key is created. This is compounded by the fact that in Ethereum there is a user using Block Explorer, as you can see how much cryptocurrency is held in all the public-private key pairs the account addresses. One example of this could be Etherscan, where you could find an account's balance and if it has sent or received anything. This would mean that the account you have found has a publicly available public key. The receiver of the coins is not vulnerable to this type of attack because it did not reveal their public key. There are obviously a lot more cryptocurrencies and blockchains out there, all slightly different and with their own different vulnerabilities, and I might go into more detail, but for now in this video I'm not. I'm going to talk briefly about the vulnerability of proof of work. If you want to go into detail, there's a whole paper in the comments, in the description, which you can just read yourself. The first paper assumes that the biggest vulnerability to blockchain technologies to quantum attack was against their EDSA digital signature. This is because it could allow a quantum attacker to hijack users' cryptocurrency. Excluding some unique cryptocurrencies like Zcash, this would only impact individual users at once. If a quantum attacker could actually attack proof of work, then they could in fact impact the entire network. For proof of work, the time complexity to verify must be much smaller than the time complexity to solve. The difficulty of the problem must be easily tunable with a parameter as well. This is to keep the block time relatively constant. Now let's talk of a 51% attack. If a single malicious entity holds more than 50% of the network computing power, then they have a over 50% chance of adding the next block. Over time, this could allow an attacker to reorganize the blockchain, immutable transactions could be changed and removed, false transactions could be added. For most proof-of-work based blockchains, these attacks are almost impossible to perform on classical devices due to extremely high network hash rates. This is one of the most damaging attacks to a blockchain. An example of this attack was against Ethereum Classic, which was a much smaller blockchain and had a prolonged 51% attack against it. A quantum attacker with increased processing power could replace the history of the blockchain if they are doing it for a long enough period of time. False transactions could be added, and because the attack will have more than 50% of the blocks, they can always ensure that they are the longest chain and therefore considered the canonical history of the blockchain. So how realistic is this attack really? Because what we are talking about is one single quantum device being able to perform more computations than the entirety of the Bitcoin network, which has the highest hash rate overall. Over time, if we apply the quadratic advantages from the previous video, this could actually be possible in the future. This is predicted to exceed Moore's law, which is in fact becoming less correct about classical devices. When could this happen? The curators of the two papers below believe this could be 2047. However, according to IBM's timeline, in the next decade, we will have quantum devices that will be able to perform proof of work in some capacity. If the immutable history of the entire blockchain cannot be trusted, this would destroy the trust in the blockchain and make it essentially worthless. That's the end of part 2. Maybe I'll do a part 3 where I go into much more detail. Until then, everyone get learning some quantum mechanics and quantum cryptography. Auf Wiedersehen.